The James Webb Space Telescope has done it again, another groundbreaking find. It's uncovered a galaxy so ancient, it's forcing us to rethink the rules. This discovery could change a lot. To see why, let's rewind. Not to the dawn of time, but to 2022. Back then, the farthest galaxy we'd ever observed was GNZ11, thanks to the Hubble Space Telescope. That was a milestone. Hubble, with its 2.4-meter mirror and superb optics, pushed our view deep into space, but it had limits. Then came the James Webb Space Telescope. With a colossal 6.5-meter mirror and infrared vision, perfect for detecting the stretched, primordial light of early galaxies, Webb didn't just follow Hubble's lead, it shattered records. In one of its first campaigns, it spotted a galaxy called GSZ-140. That galaxy held the crown for the most distant confirmed object, with a redshift of 14.32. Redshift, simply put, measures how much a galaxy's light has been stretched by the universe's expansion. Higher redshift means older light. Then came MOM Z14. With a redshift of 14.44, it pushed our view even further back in time. But it wasn't just the redshift that shocked scientists, it was the galaxy itself. MOM Z14 is tiny, only about 500 light-years across. For perspective, the Milky Way spans over 100,000 light-years. Yet MOM Z14 shines brilliantly. Galaxies this early should be faint and elusive, not this one. MOM Z14 is blazing with newborn stars, a furious stellar nursery in the opening chapters of cosmic history. And one missing feature made it even more puzzling. There's no sign of a supermassive black hole. That's unusual because most galaxies with intense star formation have one at their core. These black holes are believed to be key players in galaxy evolution, regulating star birth, shaping structure, and driving growth. But MOM Z14 breaks that pattern, and the surprises don't end there. When astronomers used JWST's spectrograph to study its light, they found something unexpected, an abundance of nitrogen. Not just a little, an unusually high amount. This chemical signature resembles what we see in some of the oldest star clusters orbiting the Milky Way, hinting that MOM Z14 is forming stars in extremely dense environments. That's not what theory predicted. Galaxies this early should be chemically simple, made mostly of hydrogen and helium. Yet MOM Z14 suggests multiple generations of stars had already lived and died before it. That means galaxy evolution may have kicked off far earlier than we thought, and it raises a big question. How many more galaxies like MOM Z14 are out there? Before JWST, we assumed such galaxies were incredibly rare, but now we're finding more than anyone expected. These ancient, brilliant galaxies, sometimes called little red dots, are popping up all over JWST's surveys. MOM Z14 might hold the record for now, but probably not for long, and that's where things get exciting. The deeper we look, the more surprises we uncover. Every discovery chips away at old assumptions. If galaxies like MOM Z14 were common, formed stars faster, and were chemically richer than we imagined, what else are we missing? Does this challenge our cosmological models? Absolutely. Our current framework says galaxies this early should be rare, slow-growing, and simple. MOM Z14 is none of those things. It's fast, bright, and chemically complex. It's not that our models are wrong, they're just incomplete. MOM Z14 hints that the early universe may have been far more dynamic than we ever imagined. And this is only the beginning. Later this decade, the Nancy Grace Roman Space Telescope will join JWST in exploring the early cosmos. Roman will scan vast regions of the sky with incredible precision. Together, these observatories could uncover hundreds, even thousands of galaxies like MOM Z14, each one a time capsule from an era we're only starting to understand. For now, MOM Z14 stands as a milestone, a flicker of light from when the universe was still finding its footing. But the deeper we dig into JWST's data, the more the universe defies expectations. Some scientists have even floated a bold idea that our entire universe might exist inside a black hole. Recent research adds another twist. Most galaxies appear to rotate in the same direction. By analyzing the curvature of their spiral arms, astronomers can determine their spin, and the pattern isn't random. In a truly random universe, spins should be evenly split between two directions. This surprising alignment contradicts current cosmological models and may hint at something profound. that our universe itself could be inside a black hole. To grasp this, we need to revisit black hole physics. When matter collapses under gravity, it forms an event horizon, a boundary beyond which nothing escapes, not even light. Anything crossing that threshold is lost to outside observers. What happens inside remains a mystery. And that's where black hole cosmology steps in, also known as Schwarzschild cosmology. This idea proposes that our observable universe might actually be the inside of a black hole within a larger parent universe. Now think about the Big Bang. The standard model says the universe began as a singularity, a point of infinite density, just like the core of a black hole. If that's true, then the Big Bang wasn't an explosion in empty space. It was the moment matter collapsed into a black hole, creating a new universe inside. And here's the kicker. Every black hole in our universe could be a gateway to another baby universe. This could even explain why the fundamental constants of nature seem fine-tuned for life. Black holes that produce stable universes might be more likely to survive and replicate through this process. Scientists believe this concept could solve several cosmic puzzles. For instance, black holes have enormous entropy, which matches the staggering amount of information in our universe. Another piece of the puzzle is torsion. In extended versions of general relativity, like Einstein-Cartan theory, torsion accounts for particle spin and can influence space-time curvature. Some theories suggest this twisting effect could create a repulsive force at extreme densities, preventing singularities from forming. If that's true, instead of collapsing into an infinitely small point, a black hole might experience a big bounce, where its core rebounds and expands outward, potentially creating a new universe inside. Rapid recoil after such a bounce could explain our expanding universe, the event we call the Big Bang. So instead of a singularity exploding from nothing, it could have been a rebirth from the heart of a black hole in a parent universe. This theory would radically reshape our view of cosmic origins, suggesting an endless cycle of self-replicating universes. And there's another twist. The universe might even have a preferred axis. Studies of large-scale cosmic structures reveal a curious alignment in how galaxies are arranged and move, far from completely random. This phenomenon, known as cosmic anisotropy, challenges the long-standing cosmological principle, which assumes the universe is uniform and isotropic on the largest scales. If the universe does have a preferred direction, it could point to unknown physics, perhaps tied to how our universe formed inside a black hole or how fundamental forces behave on the grandest scales. Adding to the puzzle, the discovery of massive ancient galaxies so soon after the Big Bang defies our current models of cosmic evolution. While the black hole universe theory is fascinating, there might be simpler explanations. Maybe some of our earlier measurements, like the Milky Way's rotation speed, are off. Either way, the universe is proving to be far stranger than we imagined. These unexpected galactic rotations will likely push astrophysicists to revisit key assumptions about how the cosmos works. What do you think? Share your thoughts in the comments below. And don't forget to subscribe to Cosmic Chronicles, because this is your space. See you in the next video.